Hello, we're Team 42 and our project is on aircraft maintenance prediction. Throughout their operational life, aircraft components naturally degrade, which affects both their performance and reliability. In light of recent controversy with Boeing, it underscores just how critical engine maintenance is. This machine learning project was developed to create a framework that predicts the remaining useful life, or RUL, of aircraft engines using comprehensive life cycle data. Our goal is to enable proactive maintenance strategies. This not only ensures aircraft operate at a peak efficiency, but also enhances overall safety. Our project goals are straightforward. First, we'll familiarize ourselves with the data. Then, we'll devise strategies to forecast maintenance needs. Next, we'll build and assess baseline models. Finally, we'll refine these models for greater accuracy and reliability. We have a dataset consisting of multivariate time series from different aircraft engines. Think of it as a comprehensive view of a fleet's health. Each engine begins in a healthy state and develops faults over time. Our goal is to analyze this progression to predict where maintenance is needed before a potential failure. The table here shows operational settings and sensor readings that we'll use to build our predictive models. In this graph, we observe the fluctuations in sensor readings for engine ID 1. Initially, the sensor values remain within a similar range. However, as we approach the end of the timeline, correlating with the failure cycle, there is a noticeable variance with our values either increasing or decreasing significantly. In this slide, we're looking at a histogram that illustrates the distribution of engine life cycles before failure. We see that most engines tend to fail after reaching a certain number of cycles, with the highest frequency of failures occurring around the 200 cycle mark.
Okay, so for this data set, doing a simple binary classification is not enough because always the failure happens at the last cycle. So if you do a binary classification, you will have a lot of class imbalance. And this is the reason why we built a new feature called as RUL, which is the remaining useful cycle. At any given point of time, it tells how many more cycles it has before reaching the failure point. And the way we calculate RUL is with this formula. We take an engine, we see the last cycle, which is the failure cycle, and then from that we subtract the current cycle, and that's how you would get the RUL. We use this RUL feature in classification and in a regression model. Uh, once we built our once we built our RUL value, we built a correlation heat map to understand how the sensors are related between themselves. And as you can see, there is a positive correlation and there are negative correlations. For example, if you see S20 and S21, they are highly correlated. That means when the RUL value increases, the sensor values increases as well. So which means in our training model, we can ignore one of the sensors since they both give the same amount of information. Similarly, we can see a negative correlation between S2 and S3. Uh, for our baseline KNN model, we created three bins. From our data analysis, we understood that whenever the RUL values are less than 100, there are more probabilities of the engine having a failure. And so we created three engines based by categorizing the RUL values. If its RUL is less than 30, it would be high risk. If it's between 30 and 100, it would be moderate risk. And if it's greater than 100, it would be safe. Based on this, we were able to get a training accuracy of 74.9 and a validation accuracy of 78.2. Moving on, in the next regression model, instead of classifying or predicting the labels, what we try is we try to get the value of RUL by using regression. And for this, we went with random forest regressor. And here is a configuration on which our regressor ran by using 50 number of estimators, max features of 3, and a max depth of the decision tree was 7. We were able to achieve an R2 training score of 0.7 and an R2 validation score of 0.4. Moving on to the baseline results. So we compared the results on how our KNN and our regressor was performing. You can clearly see how KNN has predicted most of the, especially when the predicted label is risk and the actual label is risk, it has predicted most of this label. So from this, we can conclude that the classification route is giving us better performance.
Now, coming to our proposed model, we propose to use a LSTM model because they generalize better over time series data. So we have also created a new feature called failure within window, where if the RUL value was less than 30, we would set it as true, otherwise false. This would help us to transform this problem into a classification problem. Now, coming to the architecture of our solution, we have a total of three layers. First two layers with LSTM with dropouts, and the final layer, dense layer with max pooling. So once we ran the model, these are the results we have gotten. As you can see, the graph between predicted and actual values, there's a strong correlation with it. So going to the results from the confusion matrix, we can see that we got a high F1 precision and recall scores, all of them above 90%. Now comparing the results with at the baseline, we can see there's been a strong improvement, and also we were able to generalize better with LSTM. So our conclusion is that LSTM generalized better over time series data, and also by using our synthetic features, we were able to better approximate the model. Thank you.